Good morning, everyone. Welcome to our talk. My name is Desmond Liu Zhenyuan. Today, I'm going to be presenting our work on worst-case rigidity analysis and optimization for assemblies with mechanical joints. And this work is done in collaboration with Hu Jingyu, Xu Hao, and Fu Jiwing from the Chinese University of Hong Kong, and Song Peng from Singapore University of Technology and Design, and Zhang Ran from Hasso-Plattner Institute, and Bian Bickel, who's my current advisor at ISTA. Okay, so let's begin with a little bit of introduction of what's going to be at the center of our stage today, which is the assembly structure. So assembly structure is like ubiquitous in our daily life, and people are making use of it to build like all different kind of amazing things, from like very complicated mechanical objects, like this car engine, or like deployable structures like foldable tables, foldable chairs, and toys as well. Like people can use Lego technique to build an airplane. However, when it comes to reality, there's a very important concern we need to address when we're trying to deploy the structure we just designed to the real world, which is the structural rigidity, because that's one very important factor of how durable the structure is, and that's what the end user usually care about. So like suppose we're the designer of this kind of assembly structure to be deployed in some children's playground in a park. And as the designer, I think it's kind of important to ask these two questions. So how rigid the assembly structure I just designed is, and if there's a way to make it more rigid. Because this is important to say we have like two very similar design, like which one is better when the kids are doing crazy things to our assembly structure so that it wouldn't deform a lot, it wouldn't break, it would fall apart, right? Because if that happened, I guess the kids' parents are gonna be super mad about you. So we wanna design rigid assembly structure. However, rigid assembly structure are kind of hard to design. It's not like a very straightforward task. And one of the most important challenges here is the mechanical joints in the assembly structure. So mechanical joints, they're not just like connecting different parts together, but at the same time, they will also allow specific relative motion between the parts it's connecting. Like for example, on the slides, we're showing like few examples of mechanical joints in both 2D and 3D. Like you can see in 2D, we have like hinge joint, prismatic joint, and sliding joint, and each one of them has different combinations of rotational degrees of freedom and translational degrees of freedom. And there are like all different kind of like combination of these. Like in 2D, it's kind of simple. Like in 3D, it's even more because we have up to 3 rotation and 3 translational degrees of freedom. So it's not a trivial task to come up with a systematic way to model like joints of different combinations of rotation and translational degrees of freedom. And this is not the end of the story of how like tricky the mechanical joints is to model. There's another thing we need to address. So let's check out this example. So we have like this 2 Lego parts like putting side by side, and we're using 2 hinges to connecting them. So we just use our common sense like to reason about it. Well, we say, okay, this is like pretty much stable, rigid, right? Because we have 2 hinge, and they will cancel out all the relative translation and rotation between the 2 parts, right? Because we have 2 hinge putting side by side to connect them. But let's check this out. This is a video clip, so hope it's working. Oh, great. So you can see like when we're just trying to bend this very simple assembly a little bit, you can see it's not like totally rigid, right? Especially around the joint, it deformed quite a bit. So this is something really kind of tricky to address, and this is due to a very notorious effect called joint jitters. So this can come in for many reasons, like the joint itself, maybe it's not like, the material is not very rigid, it's kind of soft, or like there's some fabrication error so that they will cause the joint like shake a little bit. And that will be a big problem if we want to target like assembly structure in real world, which may have like more than 100 joints. And this can be a big problem if we want to make the whole thing very rigid. So in this work, we're also trying to model this kind of effect. And before we move to our method, let's just quickly go through some related work to see if there's some prior technique to address the issue we're trying to solve there, which is the structural rigidity of the assembly structure. So the first thing we might think of is to use the tensegrity model. It's a very classical model from classical rigidity theory. So in this kind of model, the parts are usually modeled either as incompressible bars or inextensible cables. But this might not be the best solution to our problem because it only supports position constraints. So it's kind of hard to model all different kind of mechanical joints like with different combinations of degrees of freedom. So another thing we might think of is we can just do forward simulation using finite element method. And using finite element method can be quite powerful. You can prescribe the loads and it can compute the stress distribution. But that's also sort of like the problem because we need to prescribe the load. And We can do shape optimization on top of it, but prescribing the load sometimes is not very like a straightforward thing to do, especially with dealing with something like toys assemblies or like the assembly structure we talked about, like to be deployed in the children's playground. You never know like how the kids would do to your like precious assembly. So I think it would definitely be great if we can come up with something that take as input only the assembly structure itself without prescribed load, and we can model the parts as elastic bodies so that we can measure how rigid it is, and we can model different kind of mechanical joints and answer these two questions eventually. So how rigid my assembly structure is, and just to quantify it, and if there's a way to make it more rigid. And this will correspond to 3 contributions in our work. The first one is the modeling of the mechanical joints. As I said before, we are targeting like mechanical joints of arbitrary combinations of rotational and translational degrees of freedom, as well as joint jitters, which is really like a big pain. And the second one will be the worst case rigidity measure. So this will answer how rigid the assembly structure is. And we can also use number 1 and 2, and on top of number 1 and 2, we can do optimization to improve the structural rigidity of the assembly given by the user. Okay, so let's dive into our method. So in this, why my boomerang turned black? Oh, it was right? So like in this section, I'm gonna briefly talk about like how we model the parts and the joints in the assembly structure and how we cast the worst case rigidity as a minimization problem solving using eigenvalue analysis. Right, so let's begin with like the central concept in our work, which is the worst case rigidity. So before we go to the definition of it, let's do some preparation or recap from finite element method. So the first thing we're gonna do is we're gonna model the parts as elastic body using finite element method. Everything here just like from standard FEM, you can get your favorite material property into their like Young's modulus and things like that. And so for each part, we have a stiffness matrix, and we're gonna aggregate them together, putting on the block diagonal, so we can have a global stiffness matrix. And after that, we can define the elastic energy. Also, this is just standard. We're gonna model the elastic energy induced by the nodal displacement, delta x, denoted here, as a quadratic function of the nodal displacement. Yeah, so everything up to here is just standard. And after we're setting up the elastic energy, we can go to our definition of worst case rigidity. So the idea of worst case rigidity is we really want to find this direction so that we can deform the structure using the smallest amount of energy. So it's like deform the structure in the most energy efficient way. So energy efficient way, basically we want to find this direction. We deform it and it's like least effort. So if we formulate it using math language, it will become this kind of minimization problem. So we're minimizing the elastic energy induced by the displacement of the nodes and over all possible directions. So we just normalize it using the square norm. And it's gonna be like minimization problem of this form. But this is not the end of the story because we have a very important part missing, which is the joint constraint. Joint constraint, oh, here it comes. And because we're dealing with assembly structure and like all the hassles around mechanical joints, so we have to take that into account. So just to remind you, we're dealing with mechanical joints of arbitrary combinations of rotational and translational degrees of freedom. And there are so many of them, so how can we get started? And actually, our observation, our strategy is rather than consider how the joint allows specific relative motion, we'll think of it the other way around. That is like how the joints eliminate or cancel different relative motions. So take the hinge, for example. So hinge will allow like 1 rotational degrees of freedom with respect to the rotational axis, right? But when we're trying to model the constraint, we'll think of it the other way around. So how the hinge will cancel 3 translational degrees of freedom and the other 2 rotational degrees of freedom. And here we're gonna briefly like just walk you through like the steps of modeling the joint. So first we're gonna sample some nodes from the parts you already got from the FEM modeling. And we're gonna reason about what's the allowed motion of these nodes by the joint. So that will usually like consist of 3 parts, like the rigid motion of these nodes and allowed relative motion in the hinge. In the hinge case, it will just be like relative rotation and also individual part deformation. And after we have all the allowed motion by the joint, we can just take the null space or like the complementary space of all the allowed motion. That will give us the motion that is not allowed by the joint, which is the motion we want to cancel out from the solution space of our minimization problem. So if we do this for each one of the joint and aggregate them together, we will get set of linear constraint of this form, a delta x equal to 0. And so that will be the joint constraint. And it looks quite plausible because we find like all the motion that is not allowed by the joint and kick it out from the solution space. However, this is not really sufficient because we haven't touched a very important thing, which is the joint jitter we mentioned before. So like, for example, like this example, we have this hinge joint, which is supposed to cancel all the relative translation between two parts. But as you can see on the figure, there is some translation happening there, right? So if we just use hard constraint, like a delta x equal to 0, so like it will just prohibit like all the relative translation, but this is actually happening in real world, so we're over-constraining the problem. So in order to tackle this, we're gonna change the hard constraint a little bit. We're gonna make it into energy penalty, so make it into a soft constraint. So the way we're gonna do it is we're just gonna square it into a quadratic function of the nodal displacement. And in between, we can also add in this matrix S to control like the weights for each degrees of freedom. So you can imagine that like, if the corresponding weight is very large approaching infinity, basically the corresponding constraint would just act as a hard constraint, totally ruled out from the solution space. But if it's kind of small, like approaching 0, like the corresponding joint is very soft and easy to deform. But like because we have weights here, so it's very important like how can we choose the appropriate weight, right? And we have a data-driven approach presented in our paper so that we can match the simulation with the physical experiment. So if you want to know more details, please check out our paper. And after we're doing this, we can call the guys in the middle J, and then we can add the energy penalty term back to our energy function, so reduce it back to its initial form. And it is very well known that we can use eigenvalue analysis to solve minimization problem of this form, and the smallest eigenvalue will become the global minimum of our minimization problem, and the associated eigenvector is going to be the minimizer. So in our particular scenario, the smallest eigenvalue is going to be the worst case rigidity measure according to our definition, and the smallest the associated eigenvector is going to be the worst case deformation. So you can see we can just get this worst case deformation for the boomerang, and that's pretty much how we model the worst case rigidity and how we solve it using eigenvalue analysis. And on the computational side, there are also like two good things I think that's worth mentioning. The first thing is we're still dealing with a sparse system. Like both matrix K and J are sparse matrices. So their summation is still sparse. So we can use a sparse eigensolver to compute the smallest eigenvalue, and we only care about one smallest eigenvalue, so, and the associated eigenvector, so it can make the computation more efficient. And the other good thing is differentiable, so we can make use of this a little bit later to do the optimization on the geometry to make our boomerang looks better and more rigid. And before we move to the optimization, and there is still like a simple example of visualization I want to show you, so that I hope this can get you to have a better understanding of our minimization problem and the rigidity analysis and know what's going on there. So we have this very simple two-part assembly structure, and it's in 2D, and the top node are fixed together, like connected via a hinge joint, so that the top node can move around, and we fix the other two nodes to the ground. And we want to study, and the only node that can be moved around is like the top node, and we want to study how the elastic energy change with the nodal displacement, which is the top node. And we have this energy surface plot in the middle. So, and then we can use eigenvalue analysis to solve the minimization problem, and we can get the associated eigenvector, and you will find out actually this is also the insight like why we find this worst case deformation is like we're deforming the structure in the most energy efficient way, because the smallest eigenvector will give us the direction in which we will get the smallest curvature or smallest second order derivative. So that's why we are deforming the structure in the most energy efficient way. So I hope this will help you to understand what's going on in our method. And with this in mind, we can use our worst case rigidity to guide our optimization. So the first thing we're gonna do is, as I said before, our method is differentiable, like the smallest eigenvalue, we can get a gradient of it with respect to the design parameter of the boomerang, the assembly structure. So the craziest thing we can do is we can just move the parts around. So in this case, we parameterize the boomerang via the endpoints of the supporting bars shown in blue. And we can just change its position to get to a better configuration, which has a stronger rigidity. And later I'm gonna show some physical validation of this, so no, it's not just like a shabby PowerPoint animation. And another thing we can do is also we can do some heuristic around the topology so that we can support, we can suggest some new parts for the user to add. So the thing we're gonna do is we're gonna compare the projection of difference of displacement per node pair. So we just take the displacement and do subtraction and project it to the parts we're trying to add, and then we just consider like all the candidates and sort them in descending order by the length of the projection, and say we give the top k candidates to the user for them to choose from, like which one to add to our assembly structure to make it more rigid. So in this case, like the longest projection will be the one on the right. Yeah, so that might be the one the user want to add to the structure. So right now we already like described like all the worst case rigidity analysis and how we do optimization on top of that and how we model the joints. So I think finally get to the result part, and we have a bunch of assembly structure which is not so rigid, or there's free motion, not rigid at all, and we're gonna like use our method to analyze them and make them more rigid. So the first thing I'm gonna show is this bird model. We're using Lego technique, this kind of toy things to build it, and we have like more than 80 parts here and 100 joints, and we're using our method to analyze it. So like the yellow arrow will be the worst case deformation. So we can use our method to find, okay, so we can add a horizontal beam to reinforce it, which is the one in blue, and we can have some video clips for comparison. So you can see, like after reinforcement, we're applying the same load as the initial configuration, and the deformation is much less. Yep. And we have an even more complicated Lego example, which is this car chassis. It's also the teaser of a paper. And we have more than 150 parts in this example, and we're still using the same idea to reinforce the assembly structure. So this is the photos for comparison. Like you can see, like before, we reinforce the assembly structure, and after we use the same loads to deform it. And the initial configuration on the left, and you can see the horizontal beam pointed by the red arrow actually like tilted quite a bit. And after reinforce it, the thing just stay horizontal. Yeah, so this is the car chassis. And then we have, this is the boomerang we already seen. And so in this case, we're using 3D printed part. And we're using Lego technique joints to connect different parts together. And in this case, because we're using 3D printing, so we can just print parts of any shape we want. And we're using gradient descent as we described before, so we can get a supporting bars from the sides towards the center. And here's the photos from comparison. Like we just apply some weights there, and the deformation is getting optimized, so the structure is more rigid than before. And here we have an even more complicated example, which is the bunny. So it's still like the same material using the 3D printing and the Lego technique joints to connect things together. And this case even more complicated because we have this silhouette of the bunny. So it's actually multi-parts and it's not rigid. So if you don't have this, do we have the pointer here? Yeah, like anything, anyways, like the inner supporting like this crosses things to support, connect different parts together. It would be not rigid, so it would be just like a lot of shaking, just couldn't stay as a bunny as we want. So, but if we just randomly or arbitrarily add in this like kind of inner supporting structure to the silhouette of the bunny, it might not be the like the best solution we can come up. So we can do the gradient-based method on top of that to change the position of the inner supporting structure, so we can get to a better configuration. So we are applying the same weight, which is a bottle of water down there, and you can see it like on the left, the initial configuration will have like more deformation. It's more perceivable. Okay, and this is the rack model. So we are using 3D printing to print both the parts and the joints. And we're still using the same idea, like our method will get the worst case deformation, worst case loads, and we can use the parts, using horizontal beams to reinforce it. And the result is very obvious. You can see the difference between two cases. Okay, and this is the final result I'm gonna show. This is the boat model. And in this case, we're using this magnetic sphere and the metal rods to build this boat model. And the initial configuration, which is the one on the top, It's not rigid at all. So like the two ends of the boat can just go up. If you just like pick them up, it couldn't stay rigid, stay its original shape. And after we're using our method, we can add these two bars in between to cancel the free motion to make the boat more rigid. So here are the video footages for comparison. I guess if you go on the right, you would prefer the one on the right instead of the left one. Okay, so that will be the last example I want to show. And before I close, there are a few concluding remarks I want to make. So let's just wrap the whole things up a little bit. In our work, we proposed this worst-case rigidity measure for assembly structure with mechanical joints, and we modeled mechanical joints with arbitrary combinations of rotational and translational degrees of freedom, and also the joint jitter effect into account. And on top of that, we can do optimization on the geometry and the topology of the assembly structure we're dealing with. And however, there's also some limitation I want to mention, and it would be cool to see them getting resolved in future work. The first thing is the functionality. So actually, when we're having this assembly structure in real world, and a lot of the assembly structure, they carry some specific functionality. So they have to move to accomplish the task, like the robot arms, right? But in our work, while we're optimizing for better structural rigidity, we didn't take into account this kind of functionality constraint. And the second thing we can do is we can introduce more types of joint into our framework, especially this kind of woodwork joint, which depend on the contact and the friction to connect different parts together. And the third thing is the friction. So in our work, we didn't consider friction, and it will also be really like a promising future work direction to consider the friction between two parts. Okay, so I believe if we can accomplish these three small tasks, that would be a huge step forward towards designing a rigid assembly structure to be deployed in real world. And with that, I will close, and thank you very much for your attention.